Today's class is on mass extinctions. So these are going back through sort of very, very long-term history, geological time, periods when there's been something that's happened on the planet that's caused an awful lot of species and genera to go extinct at once. Now, I've got two confessions here. One, I'm a huge dinosaur nerd and I have been since I was a kid. I love everything dinosaur related and things like that. So the second part of my confession is today's therefore my favorite lecture because it's one of the few attempts where I actually get to talk about dinosaurs, think about dinosaurs, and it's just a bit of a nerd out. So today's lecture is on mass extinctions and I hope you enjoy. I'm just going to share my screen. Righty, so here we are. So by the end of today's class, you guys should be able to, let's put the pointer options onto laser, describe what a mass extinction is, when mass extinctions have occurred in history, and how they've affected diversity. You should also be able to compare and contrast several hypotheses explaining the cause of mass extinctions and evaluate the evidence for and against each hypothesis. And also test patterns of survival using real data to which organisms are more or less prone to extinction. That's something I just want you to have in your head. We're not going to go through it in great detail, but we'll just touch on it a couple of times today. So before we start, I'm going to do a sort of another fake clicker question. Just think about what your personal opinion is on evolution. A, the theory of evolution is not true. All species were created at the same time. B, the basic animal and plant kinds were created and they have then micro-evolved into today's species. Evolution produces new species, but it is planned or directed by a creator. D, everything evolved from a single common ancestor and the process does not involve any form of creator. Or E, I am genuinely undecided. Just take, I'm sure most of you have already decided what your answer on this would be, but just take 5 seconds to think about which one of these best describes you, just for your own enjoyment. Righty, let's move on from here. So the first part we have to cover is, well, what is a mass extinction? Well, these are the crucial things that make a mass extinction a mass extinction. First up, it has to be a rapid event. And when we say rapid, we're talking geological time. So in geological time, it would mean 10,000 years or less. Now, that doesn't sound like a particularly rapid event. Sort of 10,000 years is quite a long time and compared to a human lifespan. But in geological time, it is literally the blink of an eye. So this has to be a mass extinction is a rapid event, 10,000 years or less, we get a big change. And also mass extinction causes extinction of a significant portion of life on the planet. Really, realistically, about 60% of species have to go extinct within less than 10,000 years for something to be called a mass extinction. And this is critical and something we'll talk about towards the end. Also, the extinction is global, including a whole bunch of different habitats. So things in the ocean and on the land and in the mountains, in the deserts, on the grasslands, in the forests, all life, bits of it have to be going extinct. And also it has to be what they call indiscriminate. So it's not just basically knocking out one type of animal or plant. It has to be taking out bits of everything. Although some types of animals and plants could be more affected, bits of everything have to go extinct. And we're going to talk a lot about in this lecture about different levels of taxonomy. So before we start, I thought I'd just do a very quick note on taxonomy. So when we talk about taxonomy, this is what we mean. So these are the orders of taxonomy. So we're going to talk here about one particular animal. This is in the kingdom Animalia. It's in the phylum Chordata. It's in the class Mammalia. It's in the order Primates. In the family Hominidae, in the genus Homo, and in the species Sapiens. Can you guess what this species is? It is, if it's going to work, it is me. So I'm in the kingdom of animals. There are 5 basic kingdoms, which is the animals, plants, fungi, bacteria, and archaea. I'm in the phylum Chordata. This means I have a backbone, I have a chordate. All the vertebrates in the world, all the fish, birds, amphibians, mammals, reptiles are all chordates. We descend from an original species that had a sort of spine down the back. I'm a mammal, so I'm in the class Mammalia. I'm a primate. I'm in there with the monkeys and the great apes, so I'm a primate. I'm in the family Homidae. We are probably the only species in the family Homidae left alive. I'm in the genus Homo, and my species is Sapiens. Humans are Homo sapiens. So let's have a look at another species. This species is in the kingdom Animalia, the phylum Chordata, the class Mammalia, the order Carnivora, the family Ursidae, genus Ursus, species Arctos. It is a bear. And you can see that on this sort of broad taxonomic scale, we're actually quite closely related. So we sort of split somewhere around order, family order levels where we start to split. So that's a bit about taxonomy, because we're going to be talking today, when we talk about taxonomy at the family level. And the family level is highlighted back here. We're talking about extinctions at this level. So it's 2 levels above species. So it's not talking about necessarily just species going extinct, but entire families of organisms, which are groups of genera, and each genera contains multiple species. So over time, in the fossil record, we see 5 historical mass extinctions. So in this figure here, on the x-axis we have time. We're here at 0 years ago, and we're going all the way back to 600 million years ago. So we're going back a very, very, very long way. And on the y-axis, we have the percent extinction, so how many families went extinct. Now, there are many mass extinctions that took place. This one here in this is the Cambrian era, donated by this C. This was a very, very bizarre period in evolution, and this is still very heavily debated about what actually went on. And this is not actually considered a mass extinction because it takes so long. So although there's been a big loss of families, the Cambrian explosion and extinction took longer than 10,000 years, so it's not considered a mass extinction. The mass extinctions we're actually going to look at are these 5 here. So this is basically now, this is the present. We're going back through history. And in order of first to last, the extinctions went the Ordovician, which is this big spike in the percentage extinction of families. Then we have the Devonian, this next big spike in the percentage extinction of families. Then we have the Permian, this big extinction here. Then the Triassic, and then the Cretaceous. Okay, so we have these 5 big mass extinctions through time. These are the ones we're going to talk about today. So I don't know how much anybody knows about geological time and going back through the prehistory, but I thought I'd have one little quicker question before we got started hardcore, which you can actually discern and work out from this graph, but we will see who gets it. So let's have a quick question. So the mass extinction that killed the dinosaurs, so the most famous mass extinction you would imagine in sort of popular culture is what we call the KT extinctions. This was the extinction that meant there were no more dinosaurs. Prior to this, there were lots of dinosaurs. After the KT, there's no dinosaurs at all. So the mass extinction that killed the dinosaurs was, A, was the biggest ever. B, meant animals could evolve for the first time. C, happened before birds appeared in the fossil record. Or D, none of the above. Just give you 10 seconds on this one. 3, 2, 1, stop. Okay, so what is the answer? Well, was the mass extinction that killed the dinosaurs the biggest ever? No, it wasn't. Not in the slightest. It wasn't even the second biggest mass extinction in terms of number of species that died. Did that mass extinction mean that mammals could evolve for the first time? No, mammals coexisted with the dinosaurs for a very long time. There were mammals in the fossil record for many millions of years before the mass extinction that killed the dinosaurs. Did it happen before birds appeared in the fossil record? Again, no, birds coexisted with dinosaurs for a reasonably long time. So, and we can talk more about the relationship between dinosaurs and birds at the end, and that's actually one of my favorite parts of the class. So the correct answer is actually D. none of the above. So the mass extinction that killed the dinosaurs wasn't the biggest, didn't allow mammals to evolve for the first time, and also it happened after birds had already appeared. So now we've talked about that a little bit, we'll come back to that at the end, but let's have a look at the extinctions in turn. So the first real mass extinction was called the Ordovician extinction. And this mass extinction occurred about 450 million years ago, and it signaled the end of the Ordovician period, this part here. Okay. And what caused this mass extinction? Well, based on geology and tectonic plates and their movement, what is suspected to have happened is that there was an intense ice age associated with the supercontinent. So at this time in prehistory, all of the land mass, just by sheer chance, ended up basically on one of the poles. The movement of the tectonic plates was such that all the land mass sat on the poles. Because the land mass was on the poles, it meant that as snow and ice formed, it formed this massive white sheet. That white sheet then reflects an awful lot of the sun's rays, which leads to the Earth getting even cooler, and we get this gigantic ice age. That ice age meant that most of the Earth's water was tied up in this massive ice cap that sat on all of the land, and that led to a huge decline in sea level. As a consequence, we think about what died in the Ordovician extinction. So in total, about 85% of marine animal species died in the Ordovician extinction. If you remember at the beginning, we said that the Ordovician mass extinctions had to be associated with deaths in multiple extinctions in multiple different ecosystems. We didn't talk about terrestrial animals at this time because, well, basically there really weren't any. There weren't that many at all. At this point, most of the life on Earth, the vast majority, lived in the oceans. And with the Ordovician extinction triggered by this gigantic ice age, about 85% of marine animal species went extinct, including these entire families of trilobites, never seen again, and also a very weird and unique sort of mollusk that was this sort of flat giant shell. Nothing like it has ever been seen again. So about 85% of marine animal species died. What survived? Well, the two really big things that survived that were important for our story were the placodermi. These are jawed fish. So these are these absolutely enormous, I mean, here's a human for scale, like proper legitimate nightmare fuel, these gigantic, enormous, bony-headed jawed fish called the placodermi. They survived the Ordovician extinction, as did the lamprey, one of the oldest sort of fish on the planet. These don't even have a jaw, they have a round sucker. These are the fish that are causing absolute havoc because they've invaded the Great Lakes and they're munching their way through a load of the fish there. So they're pretty nasty things even now, but they survived the Ordovician mass extinction. They're that old. The fact that the jawed fish survived meant that there were now jawed fish species left and from those original jawed fish species, all the other fish that we know today could actually evolve. So after the Ordovician and the mass extinction, we then move into the next major era, was the Devonian period. And the Devonian period was important because some very unique organisms that are important for the rest of our story actually first turn up in this Devonian period. So the Devonian period is, well, the centroid of it is about 400 million years ago. It spanned about 380 million years, well, 420 million years ago to about 370 million years ago. But it's associated with some very important species. One of the major ones are the lobed fin fish. So these lobed fin fish are unique because unlike most of the fish that you know, they actually had bones in their fins and they form these thick fins. Now these lobed fin fish, one of them in the Devonian period evolved to become this species called Tiktaalik. And Tiktaalik is very interesting because Tiktaalik is thought to be the ancestor of all land vertebrates. So Tiktaalik shares many characteristics of a fish. It has fins, it has scales, but it also shares a lot of characteristics of land vertebrates. Specifically, the head looks very much like a salamander, or another sort of amphibian. The position of the eyes, the way the eyes work, very, very amphibian-esque. And the structure of the bones inside this fleshy fin are very, very similar to the structure of the bones inside amphibians, inside reptiles, and inside you and I's hands. So Tiktaalik was very important because it became the ancestor of all land vertebrates. It was descended from this species of lobed-finned fish, and it went on eventually to become all land vertebrates. We'll talk more about lobed-finned fish throughout this talk, but they're really kind of crazy things. Most of the fish that you think of today are what we call fin fish, or ray-finned fish. The difference is in a ray-finned fish, they don't have this sort of bony, fleshy structure here. The fin tends to be attached directly, and most of the muscles are attached to the fin themselves rather than the flesh, rather than the bones. Okay? But the Devonian period was associated with the Devonian extinction. So the Devonian extinction sits here. It signaled the end of the Devonian period. And what caused this extinction? Well, it occurred in the fossil record about 370 million years ago. And what caused it? Well, this one's pretty clear cut. It was an asteroid. So there is still the scar of this asteroid is in the world today. It sits in southern Sweden. You can go and visit it. I've actually visited these absolutely beautiful lakes that it left behind. But the asteroid slammed into the Earth and it left this very ring-shaped scar. The age of the rocks in this scar lines up exactly with the sort of the mass extinction that's observed in the fossil record associated with the end of the Devonian period. So it looks like this asteroid smashed into the Earth, left this huge scar and led to the extinction. How did it do this? Well, what happened was as the asteroid hit, it threw an awful lot of dust into the air. This meant that the sunlight could not penetrate. Because sunlight couldn't penetrate, it meant that plants and algae in the ocean could not photosynthesize. This meant no oxygen was produced in the water. As a result, the oceans went anoxic. There was no oxygen left in the oceans. That choked things. In addition, we had fluctuating sea levels because all the land got sort of wobbled around. The dust in the air also led to a huge period of global cooling. We got altered biogeochemical cycles due to the origination of photosynthesizing plants, and we got enormous volcanic eruptions. Generally, not a good thing. Okay. So what went extinct in the Devonian period? Well, a lot of things. About 75% of all species on the planet went extinct at this point. Some of the things that we never saw anything like it again. We saw 3 groups of trilobites all went extinct. Tiktaalik, unfortunately, went extinct as well. There's no fossils examples of Tiktaalik until after the Devonian extinction. Fortunately, at this point, Tiktaalik had already evolved into a few other species. It itself didn't make it, but some of its descendants did. In addition, the Sarcopterygi, most of the lobe-finned fish, the vast majority of them went extinct. And so that was the end of them, which was quite unfortunate. What survived? Well, critically, no shark greater than 1 meter in length, about 3 feet. No shark longer than 3 feet survived the Devonian extinction. But some of the most critical, so a small tetrapod. Tetra means 4. Pod means feet. So a small 4-footed animal survived. This tiny little tetrapod was about 10 centimeters long. So that's about, what's that in inches? That's about 3 and a bit inches. So a tiny little thing about this big. This small tetrapod that had descended from Tiktaalik survived. Because this little tetrapod made it through, this tetrapod then evolved into all the land vertebrates. All land vertebrates radiated out from this one species, so it meant we have every amphibian, every bird, every mammal, and every reptile. All can be traced back to this tiny little tetrapod that luckily managed to get to the Devonian extinction. If this little species hadn't made it, who knows what would have evolved instead, because we didn't have this as a base. There are some other interesting things that made it through. So some lobed-finned fish did make it through, although we don't think of these as being particularly common because they're just not anymore. But some of the classic ones are the Queensland lungfish from Australia. This is a classic lobe-finned fish. It looks exactly like the one from the fossil record. It's got the sort of big scales, the head that looks slightly amphibian, and it has critically these big fleshy fins, and it can actually walk around. The reason this thing is so amazing is that it lives in parts of Queensland where the rivers often dry up for years at a time. And this animal can bury itself in the mud at the bottom and be encased. And as long as it makes itself a little air tube, it can sit and breathe air, a fish that sits and breathes air, for a long period of time until the water returns. One of the most staggering examples that turned up is a fish called the coelacanth. So the coelacanth is another species of lobe-finned fish, but unlike the Queensland lungfish, which lives in rivers that perennially dry up, the coelacanth lives in very, very deep water. So it's very, very sort of deep sea fish. This one that's been photographed with a diver, you can see how shocked the diver is. This one is probably going to die. They only ever get seen in shallow water, especially water shallow enough to dive in, when they're on their way out. They're basically lost. But what's really interesting about the story of the coelacanth is it is a great example of a living fossil and a rediscovered fish, because coelacanth was known in the fossil record. Coelacanth fossils and fish that look like this are actually very common in the fossil record. People had known about these for ages, and they just assumed the coelacanth had gone extinct about 75 million years ago, because that's when its numbers dropped off a lot in the fossil record. So people had always thought this fish was totally extinct and it was just a fossil. And then in the mid-20th century, a fisherman in Indonesia pulled one up in their nets. They literally pulled up their nets from going fishing, and there was a coelacanth in it. The guy who pulled it up had absolutely no idea what he was looking at, but was like, oh, well, it looks kind of interesting. So he sent it off to a museum. That museum eventually sent it off to the Natural History Museum of London, which at the time was the sort of main seat of knowledge for these things. And one of the people at the Natural History Museum instantly recognized it. It was like, that is a living coelacanth. This is a fish that they thought had gone extinct for 75 million years and then turned up in a fishing net. It was quite a story. But these things survived. These are nice little conversation pieces. This was critical to the trajectory of life from now on. So after we had the Devonian extinction, we went through this sort of long period without a mass extinction. And these were two periods called the Carboniferous and the Permian. So the Carboniferous and the Permian were this era when, the reason it's called the Carboniferous is because the oxygen levels in the air at that point were so big that it was this insane period of growth. So lots of new species appeared and lots of really kind of bizarre species started turning up in the fossil record. And the Carboniferous and the Permian period were very interesting for one major reason. And this was a reason where on the land, so in the terrestrial area, we started to see very large land animals for the first time. And specifically, the era was characterized by what we call the mammal-like reptiles. So this is one of the most charismatic, was a large predator called Dimetrodon that had this huge sail on its back. It was a huge, terrifying predator. It got very, very large indeed and was probably the top predator of its day. But these animals were reptiles. I mean, they have scaly skin, you can see from the fossils, but they also showed many what we call mammalian characteristics. So although they were clearly reptiles, the gait, the way they stood, was much more like mammals that we see today compared to other reptiles. And critically, the structure of the head, especially the jaw and the teeth, looked an awful lot more like the mammals of today than it does the reptiles of today. So these were what they called the mammal-like reptiles. They weren't true dinosaurs. They were reptiles that were sort of evolving towards becoming mammals. It was a very interesting period. However, the Permian period was ended by the Permian mass extinction. And the Permian mass extinction is quite a controversial one. It's still not been fully agreed upon as to what really caused it. It's thought to have been volcanic eruptions. So if you look in the geology, the geology of the planet, at the end of the Permian mass extinction, so in the Permian period, there's this layer of hydrogen sulfide buried in the rocks. That's a very, very thin, narrow layer that coincides exactly with the Permian mass extinction. And so as a result, it's thought that this is associated with volcanic eruptions. There was a huge period of volcanic eruption. This led to global warming and anoxic oceans. The question then is, well, what caused these volcanic eruptions? There is a theory that it was caused by an asteroid or comet hitting the Earth, but unlike for the Devonian, we haven't found the scar for the asteroid. So it could be under the ocean, like who knows where it is. But it was this huge deal. The thing with the Permian mass extinction is it was an enormous mass extinction in terms of number of families that went extinct. So what died in the Permian mass extinction? Well, the short answer is almost everything. It is the closest in the entire history of this planet that life has come to being entirely extinguished. So in the Permian mass extinction, 95% of all marine species went extinct. So that's basically only one in 20 species survived. 70% of all terrestrial species also went extinct. So as a result, there was this massive extinction. It nearly genuinely drove the planet to becoming sort of devoid of life. Some of the charismatic ones that went in the oceans, the blastoids, this very bizarre species of echinoderms, which are closely related to sea urchins and starfish. The entire class went. You can see this sort of thing is it looks almost like a starfish that sat on a sea urchin. It's sort of halfway between the two. In addition, all the wall-toothed sharks disappeared, which is a real shame because these things were crazy. So these were a whole group of sharks where their jaw had actually been rotated 90 degrees, and rather than having a jaw that came out with two sets of teeth, they literally had a circular saw on the front of their mouth that it's believed as a result they could, when they attacked things, they could shear off chunks of whatever they were eating and swallow it. So pretty amazing things, and unfortunately they all went extinct in the Permian mass extinction. On the land, almost all of the mammal-like reptiles went extinct. So these are all the mammal-like reptiles. Here's Dimetrodon that we talked about earlier, the fabulously named moss chops, which was a very large sort of rhino-style terrestrial mammal-like reptile. Most of them went extinct, pretty much all of them. So of these mammal-like reptiles, there's a massive amount of extinction. So what survived the Permian mass extinction? Well, actually very little survived, but at least two very important animals managed to make it through the Permian mass extinction. Both of these animals were about the size of a house cat, so they weren't particularly big. You know, they're sort of standing maybe 10 inches high at the shoulder and less than 24 inches long. So two little nondescript animals, both about the size of the house cat. And these animals were called Nidontia and the Archosaur or Protosaurus. And these two are very, very important. Firstly, let's talk about the Archosaur. So the Archosaur, this little tiny nondescript animal that made it through the Permian mass extinction, became the ancestor of all dinosaurs and all birds. So remember, this is a phylogeny, a phylogenetic tree. If we go, we're going backwards in time. So the splits mean that something that is divided, that splits off a long way this way, are not particularly well related to each other. So the Archosaur, here's the Permian mass extinction in time. So the Archosaur had actually split off from snakes and lizards. So snakes and lizards are one group, the Squamata. And here is the Archosaur. So they'd actually split here. This split had led to the Archosaur in one direction, the snakes and lizards. After the Permian mass extinction, the Archosaur first off split into the crocodilians and everything else. So alligators, crocodiles, narwhals. They split off, and then everything else split off, and then it then split again, and we got the pterosaurs. Then we got the order Ornithischian dinosaurs, then the Saurischian dinosaurs, and the birds. So this little thing, the fact it managed to make it through, meant that we now have crocodiles, all the dinosaurs and birds. So it was lucky it got through. From our perspective, we're even more fortunate that the Cynodontia got through, because this little animal went on to become all of the mammals and everything else. So here is another phylogeny. So this is each split is a different group coming off. Here's Cynodontia, the one that made it through. And it carried on splitting and splitting, and it became the mammals. And so here are the mammals, here are the monotremes that we talked about earlier on, which are the platypus and the echidna. Then we have the marsupials, this is all the kangaroos, all the opossums, all of those things. And here is the placentilla. These are the placental mammals, which is me, you, your dog, your cat, cows, sheep, everything. Because this little animal made it through, we got all of the mammals. So these two little species getting through, so we can put these all on. There's the platypus, the kangaroo, and there's me. Because these two things made it through, we ended up with dinosaurs, birds, crocodiles, mammals, everything. Okay. So after the Permian period, bearing in mind that this massive mass extinction, we then hit the Triassic period. And so the Triassic, the Jurassic, and the Cretaceous period are the age of the dinosaurs, basically. This is when we get into dinosaurs proper. And in the Triassic period, which was the first part of the age of the dinosaurs, what do we start to see? Well, we see some really quite bizarre animals. So first of all, we get Carnifex carolinensis. This is a walking crocodile the fossils of it were discovered in the Carolinas. It looked like a crocodile, but it had these massive back legs and it walked on its hind legs and was actually a terrestrial species. We also start seeing this in the Triassic period, early no-shell turtles. So this is the origin of turtles. The turtle evolved before the shell did. So the first turtles, they start to become turtle-shaped. They show turtle heads and things like that, but they don't have shells on them. Also, we start to get the early sauropods, the big, gigantic Brontosaurus, Brachiosaurus, Diplodocus, those big, enormous sauropods. And these were truly giant. They're the largest land animals the world's ever seen. Here's a person and their dog, and this shows you how big these things really were. But the Triassic period, the first period of the dinosaurs, did actually have a mass extinction take place within it. So although the Triassic, the Jurassic, and the Cretaceous are collectively known as the age of the dinosaurs, there was a mass extinction within the age of the dinosaurs. And it was known as the Triassic extinction. It was caused by an asteroid, which led to then volcanic eruptions. And that was also associated with the breakup of the supercontinent Pangaea that we talked about in previous lectures. And this led to falling sea levels. So we had this actually quite sizable mass extinction take place inside the age of the dinosaurs. What went extinct in the Triassic extinction? Well, many large early versions of later dinosaurs went extinct. So some of the early experimentation and evolution that went on in the dinosaur group, some of the really big ones actually went extinct because that large body size, you have high energetic requirements, and you just can't make it through. Also, we lost the conodonts, which is a shame because they looked permanently surprised. They did not look happy about being involved in the Triassic mass extinction. And in total, we lost about 75% of all species at the fossil record disappeared in the Triassic. After the Triassic, we then go through the Jurassic and the Cretaceous period. This was a relatively stable period that lasted a pretty long time. And that was the point when the dinosaur evolution really started to go crazy. So within this period, in the Jurassic and Cretaceous species, we start to see things like the mosasaur, the gigantic marine reptile that was made famous by Jurassic World, this enormous, monstrous predator, one of the biggest predators the world's ever seen. From our perspective, we see something really interesting where in the Jurassic period, the first shrew-like real mammal turns up in the fossil record. So there have been fossils of these little sort of shrew-like things running about with the dinosaurs in the Jurassic period. They survived all right the way through the Cretaceous. Also, we got to see the T-Rex, which is great, Triceratops, a whole bunch of the classic iconic dinosaurs you see. and one that's really interesting, which is Archaeopteryx. So Archaeopteryx, we talk a lot about Archaeopteryx's classification at the end, but Archaeopteryx was a species that shared a lot of characteristics between dinosaurs and birds. It had the head of a dinosaur and the feathers of a bird. We'll talk about it at the end. So, unfortunately, the Jurassic and the Cretaceous were brought to an end by the Cretaceous mass extinction. This was caused by an asteroid, which is well documented at this point. That led to volcanic eruptions and associated with falling sea levels and global warming. It was a huge, in fact, I say it was a huge mass extinction. It was a huge event for the time. But if we look at the size of our mass extinctions, we actually see that the mass extinction that ended the dinosaurs is the smallest mass extinction out of our 5 in terms of percentage of families going extinct. So that's pretty staggering to begin with. But what's even more staggering is the other mass extinction that took place in the age of the dinosaurs, the Triassic mass extinction. That mass extinction is actually bigger than the mass extinction that ended the dinosaurs. So more dinosaur families went extinct in the mass extinction, but some of them fortunately made it through, allowing the age of the dinosaurs to continue until the mass extinction at the end of the Cretaceous kind of wiped them all out. So, what died in the Cretaceous extinction? Well, the big thing that died that everyone knows about is all non-avian dinosaurs. So things like the Velociraptor. I hate if anybody seen Jurassic Park, Jurassic World. They took a bit of liberties in those films as to what the Velociraptor actually looked like. This is what the Velociraptor actually looked like. It had feathers over the vast majority of its body. It had the very reptilian skull, but they've actually found the feathers on these fossils of velociraptors. It still had the big nasty death claw, which is what everyone's really concerned about, but it looked a little bit different on the films. Generally, in the Cretaceous mass extinction, everything terrestrial bigger than a Labrador dog died. So anything that lived on the land and was bigger than a standard family dog didn't make it. Some things did make it that were bigger than that, but they weren't terrestrial. So what did make it through? So what survived the Cretaceous extinction? Well, the big one that got through is crocodilians. So crocodiles, this is a saltwater crocodile. I actually took this picture up in Northern Australia. I showed it in my introduction to this class, like Professors of People 2 slides. Crocodiles, like these big saltwater crocodiles, have remained pretty much unchanged since the age of the dinosaurs. So these crocodiles were using the same hunting technique they use now to pull velociraptors into the water. The reason they're so successful is because a crocodile is a very large predator, and the way it hunts is it just sits near water because it knows that every single animal in the world has to come to water to drink. It just sits in the shallow water, waits for something to come and drink, bites it, pulls it into the water. And crocodiles have a really crazy metabolism, which means that if they eat one large meal, so for example, the crocodiles in Africa right now, if they're able to catch one wildebeest, they often don't need to eat again for an entire year. So this means if you're in a mass extinction, if you're a crocodile, as long as you get one good meal, you can actually survive a year without eating again. So they made it through the Cretaceous extinction. The platypus, there were platypus-like mammals turning around and other small mammals. They made it through the Cretaceous mass extinction. Turtles, fortunately, made it through. And small avian dinosaurs. So I've talked this word about avian, you might have heard of as a word that's often used to describe birds. So small avian dinosaurs. And I wanted to take a little bit of an aside right now. So on a side note, what is the relationship between dinosaurs and birds? Well, let's do it on a clicker question. A, birds and dinosaurs are not closely related. B, birds evolved from dinosaurs, but it took a long time. C, birds are dinosaurs. Just give you 5 seconds to ponder that one, and just a bit of soul searching as much as anything else to go through. So what is the answer? Well, currently, according to most taxonomists, we are looking at Answer C, birds are dinosaurs. There is no two ways about this, really. Let's have a look at the phylogenetic tree. Because birds didn't evolve from dinosaurs, birds are a type of dinosaur. So this is our phylogenetic tree of all the dinosaurs. We've got stegosauruses, ankylosauruses, pachyderms. We've got this is all of Triceratops, Strachiosaurus, all that sort of lot. Here's all our sauropods. And then we've got, this is all of the T-Rex, Velociraptor group down here. So remember, on these phylogenetic trees, the later off you are that you split from something, the less closely related to it you are. So here's everything, and here are our birds. Our birds evolved from a type of small predatory dinosaur, a bit like a velociraptor. So here's the true birds down here. So the birds you can see are included in with T-Rex, velociraptor, and all those sorts of things. So would you consider a T-Rex a dinosaur? And would you consider a Stegosaurus a dinosaur? Well, yes, when we think of them, they're both dinosaurs in our heads. A Stegosaurus is a dinosaur and a T-Rex is a dinosaur, in the same way that a Brachiosaurus, a big sauropod, is a dinosaur, and a Triceratops is a dinosaur. So if you're willing to say that a T-Rex and a Triceratops are both dinosaurs, you have to taxonomically also say that birds are dinosaurs, because birds are more closely related to T-Rexes. So here is the split. This one led to T-Rexes. This one eventually led to birds. Here is the split, the common ancestor of T-Rexes and birds. But the common ancestor of T-Rexes and Stegosauruses isn't till back here. So that means a bird is much more closely related to a T-Rex than a T-Rex is to a Stegosaurus. So as a result, they're included in with the dinosaurs. They didn't evolve from them. They are part of the dinosaurs, which is kind of cool. It means you can go out and, you can put a little feeder out on your back deck, and you can put seed in it, and you can feed the dinosaurs, which is kind of fun. They're small, about that big, and they're flying, but technically they're dinosaurs. There's not just this episode from phylogeny. We can actually look at the fossil record. So that in the recent years, there have been some absolutely phenomenal fossils found. So this is a fossil of a baby velociraptor-style animal. You can see the bones are incredibly well preserved. But what's really critical is, as well as the bones, the entire animal down its back has this layer of what are feathers. They're little tiny short fibers with little fibers sticking off the side. They're basically feathers. This animal, the velociraptor, had feathers, at least a stripe down its back. And feathers are universally seen as a bird characteristic. So the dinosaurs and birds, it's very hard to make the distinction between them. Now, this was an astonishing find when it was first found, but this is a fossil. And if you know anything about the way that fossilization takes place, an animal dies or a plant dies, it often falls into a riverbed, sediment goes over the top of its carcass, and through that sediment, minerals impermeate into the bones, and they basically form, essentially, it's an echo of the bones. So the bones that you see in a fossil, the compound that they're made of is not actually the bone itself. It's minerals that have gone into the bone and so formed a sort of clone of the bone. But there's one difference, and that is amber. So amber is when a tree gets a wound and the sap ekes out of it. That sap can actually become compressed and turn into rock. And the thing about that sap fossilizing is it preserves whatever is inside it perfectly. So this is, the plot from Jurassic Park, the mosquito preserved in amber. Well, a few years ago, somebody found a piece of amber that contained something really staggering, and that was this tail of a baby velociraptor-style dinosaur. So this is the tail of the velociraptor, and you can see the actual feathers still encased in the amber with the ants. And the critical thing about this is, this fossil, you're not looking at a cast of the feathers or a reproduction of the bones. You're actually looking at the flesh itself. So these are the actual feathers on the tail of a velociraptor. So it's pretty staggering, the difference. So velociraptors had feathers. Feathers, what we think of as birds. Velociraptors, are they birds or dinosaurs? Everything becomes muddled up. And then there's this one. So this is a fossil called the Archaeopteryx. I actually have a copy of this fossil in my front room, and it's one of my favorite fossils the world's ever seen. This particular specimen is called the Berlin Archaeopteryx. These Archaeopteryx species, a lot of these fossils were found in one place in China, and these incredible fossils were found, and then they copied, and multiple fossils were given to, at the time, the biggest natural history museums in the world. So this is known as the Berlin Archaeopteryx because the Chinese sent it to the German capital of Berlin as basically a gift. And the Berlin Archaeopteryx is an amazing fossil because, first of all, it's incredibly well preserved. You can see the head, there's the neck, the spine, and here are the legs of this animal, and here's its tail, and here are the front limbs with these wings. But what's incredible about this fossil is, if you look closely, you can still see the feathers on the wing of this animal. So it had feathers, so therefore surely it must be a bird. But if you then zoom in and look at the head of this animal, you can see it does not have a beak. It has jaws, and it actually has teeth. And it doesn't have any sort of beak. Its head was covered in skin and flesh, and the whole thing was very much a reptilian head. It had a head almost indistinguishable from a velociraptor. So this animal had the head of a reptile, and clearly not just feathers, but the wings of a bird. The velociraptor might have had feathers, but it didn't have wings, and it certainly couldn't fly. This thing instead had full wings, was clearly capable of flapping flight, and it had the head of a reptile. So it's this wonderful example of what we call an intermediate form. It shares the characteristics of two different groups of animals: the feathers and wings of a bird, and the head, and also the bony tail of a reptile. So I still very much subscribe to this idea that dinosaurs are birds. Finding the line that divides dinosaurs and birds, it's impossible because they share so many characteristics. Okay, one of the questions about mass extinctions that goes along at the minute is, are we entering a sixth mass extinction today? Because the background rate of extinctions of species in the fossil record is normally you expect about 1 to 10 species per year to go extinct in the fossil record. Currently, at the minute, on our planet, 70 to 700 species are going extinct per year. So that is a much higher rate than what we'd expect at background. So if we look at extinctions per million species per year, by and large, it's generally pretty low. We have these periods of very high extinctions, but we're much higher than what the background rate is. So can we then be a mass extinction? Well, let's have a look. On the x-axis of this figure, we have the extinction magnitude in terms of percentage of species. So 0 to 100 extinctions. On the y-axis, we have lots and lots of different groups of animals. So we've got the mammals, the aves, the birds, the reptiles, amphibians. These are all the fin fishes, the Archaeopteryx. These are mollusks, bivalves, and then we've got sharks and decapods, lobsters, crabs, all those sort of things. This is their current rate of extinction, where they're sitting now. This number is their background. So this is how many of species have gone extinct due to humans. For it to be a mass extinction, you need to be hitting 75%. And we're looking at, we have not managed that with any one species yet. So this is the 75% that needs to be qualified for a mass extinction. Here are all of the classic mass extinctions through time. So we've got the Ordovician, the Devonian, the Triassic, the Cretaceous. So here's all our actual mass extinctions. They all are above this line. We've not yet managed it, okay? But one thing to consider, a mass extinction has to happen rapidly in geological time, 10,000 years. We have only really been making things go extinct for a lot less time than that, if we're honest. So people have only really been able to make things go extinct very rapidly on a much shorter time frame than 10,000 years. So we've still got a lot of time to make a lot of things go extinct before we, and so that gives us lots of opportunities to push species over this line and actually enter the sixth mass extinction. So it's a bit of an open concept. But what is your personal opinion on it? Do you think, are we in the sixth mass extinction? Do you think A, everything's doing fine? B, we're driving populations of species down, but not extinct? We're causing lots of mass extinctions, but it's not yet a mass extinction? Or are we in the sixth mass extinction now? Okay. Well, I would argue, oh, that's the wrong way. We are causing lots of extinctions, that can't be debated, but we haven't yet hit that threshold of it being called a mass extinction. Okay. Now, just one thing I'd like you to do very quickly. You don't have to actually, I'm not going to mark this, so just do it as a thought exercise. You haven't got a pen and paper handy. So we talked about the mass extinctions. Okay, so this is our time. This is the present, and we're going back 600 million years. And we highlighted the mass extinctions at the Ordovician, the Devonian, the Permian, the Triassic, and the end of the Cretaceous. So we had these big mass extinctions. I want you to draw your prediction of how diversity has changed over time at the same time as these mass extinctions have taken place. So we've had this point, we've had mass extinctions happening continuously. So what happened after them? What would we expect diversity over time to look like? Now we're not looking at extinctions. Instead, on the y-axis, I want you to draw number of families. So number of families present on the planet. So what do you think happened? Well, if we look in the fossil record, what's actually happened is this pattern, which is really interesting. Because although we've seen drops in diversity at the end of these mass extinctions, the number of families. So for example, remember, we have a little drop at the end of the Ordovician. Here's the one at the end of the Devonian. There's quite a big drop at the end of the Permian, because a lot of things went extinct at the Permian. And here's the one at the Cretaceous, at the end of the dinosaurs. But generally through time, we've actually observed the number of families continuously increasing. So even though we've got these mass extinctions, the diversity of life on Earth has actually gone up continuously. In the next couple of classes, we'll talk about why that is. Okay, so just want you to remember that by the end of this class, you should now be able to describe what a mass extinction is, when they've occurred in history, how they've affected diversity. Also, you should be able to compare and contrast several hypotheses explaining the cause of mass extinctions. Okay, well, that is the end of the class this time. I hope you enjoyed it, and I will see you next time.